Okay, so yeah, I think there should be a 2 right there in that position, but it's okay. Now, what they give you is, they set you up to use the integrated rate law for second order because they tell you right here in the rate equation that, NOBR is to the second power. Um, and then they give you the rate constant, at a temperature, and then they tell you that the initial concentration is 0.1 molar. And then they ask you for the concentration of NO. That's what I missed yesterday. I was calculating the concentration of NOBR, and that's not what they wanted. So I know that I have to use the integrated rate law for second order, but I have to answer the question for NO. So let me think about that integrated rate law, and I'm going to write it down and put in NOBR. So the integrated rate law, for second order. Wow, that pen's awfully big. I don't know if I can change that. There we go. That's better. All right, so this is the concentration at some time in the future, and this NOBR over here is the initial concentration. So I can go ahead and plug in all these values. And what I'm going to calculate, and what I did yesterday was I calculated NOBR at the time in the future, 1 hour. But they ask, what is the concentration of NO? So I have to look at what I'm calculating. This guy, if I calculate this, that is going to be the concentration at that point in time, that 1 hour point. And then I have to look at the reaction itself, which is 2 NOBR goes to 2 NO plus BR2. And I could say, well, geez, if I know how much of this is left, then I can find out how much is reacted. This is how much is left or remaining. And if I can figure out how much reacted, then I can see that since there's a 2-to-2 stoichiometric ratio, then that must also equal how much NO is produced. Now, once I realize that, then I can solve the problem. I could go ahead and calculate what I did yesterday, which was to calculate the concentration of NOBR at the 1 hour mark, then figure out what it started with, what it is at that 1 hour, then that'll tell me how much reacted, and that's the answer that I have to look for in that list because they're asking for the amount of NO that's produced essentially at that hour point. So that's the idea, and that's the approach on how to solve the problem. Any questions on that?
So if they were looking for BR, would you have done it by like 1/2?
Yes, because you're gonna, if they're looking for BR2, you'd have to say, yeah, that there's half the amount that's gonna be produced as the amount of NOBR that was used. So
Okay.
yes, yeah, you're correct. Yeah. All right, so let's go ahead and plug in those values. So I want to calculate 1 over NOBR at some time. equals the rate constant they gave me is 1.0 times 10 to the minus fifth. At the 1 hour mark, which is equivalent to 3,600 seconds. And the reason why I had to convert the hours to seconds is because I have to look at the units of the rate constant, and that's in reciprocal molarities seconds. So these seconds will cancel. And so what I get is reciprocal molarities in that position, plus 1 over the initial concentration, which they tell me is 0.1, right? 0.100 with a couple more sig figs. So if I want to be careful with sig figs, I have 2 sig figs here. And so my answer is going to have 2, and that's what they're showing. All right, so what I have to do now is plug all that into my calculator, and I want to calculate the concentration of NOBR at time t. So let me do that. And if you guys have your calculator out there, you should also do it in case I make a mistake. So I get for that 0.0996 with 1 extra sig fig. Did anybody else get that?
Yes, that's what I got.
Okay, good. So now that's the amount that's remaining. So now I can calculate the amount of NOBR used. That would be the initial amount, which is the 0.100 minus 0.0996. All right, so when I do that, I get 3.59 times 10 to the minus 4 molar. And now I can make my analogy now that I argued before up here. If I figured out how much reacted, which is what I just calculated, from what was left, and I used the integrated rate law to calculate, what was left at the 1 hour mark, then that amount reacted should also equal the amount of NO that was produced, because it's a 2-to-2 ratio. And so this is the answer that I should be looking for in the possible answers, and not this one. So I think you see now that the 2 sig figs, that's answer A. Any questions on that?
How are you getting the 0.099? I keep getting 0.036.
For this guy right here, for this?
Yeah.
Okay. Let me break it down for you. Okay, let me move that back up. So 1 over NOBR at time t equals that 3,600 times 185 change signs equals this 0.036 0.036. And then the next term, 1 over 0.1, that's just 10. Okay.
Okay, I see what I did wrong.
Yeah, that's easy to get messed up there. So this equals 10.036, and that's 1 over the concentration. So the concentration's 1 over that, which is the 0.0996. All righty.
Yeah,
Oh,
thank you.
awesome. Awesome. Any other questions on that one? Or any other ones? We got all day to do these problems.
I have questions on the acids and base homework, but I know we're still going over that PowerPoint, so I can hold off on those till after if you'd prefer.
Yeah, maybe we didn't cover that material yet. Or we could take a quick peek at it and see if you want to. If you're
I could pick one that's early in the homework, maybe.
Yeah, okay.
Most of my questions have to do with when it asks to identify the strong versus the weak and that kind of thing. Because it doesn't
Okay.
seem like there's a system for it. You just kind of have to memorize things. I was wondering if you had systems for that kind of thing.
Yeah, and we're going to talk about that. Now, there's the 7 strong that you should memorize, right?
Right. And yeah, those ones I do know. It's when
Yeah.
it's more complicated, you know, when you got like a bunch of different kinds of problems all together, that's when it gets confusing.
Well, we haven't looked at the problems involving all the other possible weak acids yet, and we haven't introduced the weak bases and their constants.
Okay,
So
that's fine. Yeah.
yeah, maybe it'll clear up a little bit more. But okay, so let's go ahead. When's that homework due? It's not due till the 14th.
Okay.
So this Sunday is when both of the acid and base homeworks are due. There's 2 of them.
Ah, okay. And so do you want to take a look at maybe I should put off that second one because we haven't looked through all that material. And you have a question on some of the others. So let's look at the questions.
I'll just pick number 9 from the first homework because that's pretty early on in the homework and that seems pretty straightforward. And I feel that might help me answer the other ones if you help me with that one, maybe.
Okay.
Maybe.
Yeah, sounds good. Sounds good. So it's this one here, chapter 14.
Yes, just the regular, not the equilibrium one, but the acid and bases.
Okay.
Most of them are pretty straightforward, just like solve for pH or solve for concentration, but the ones where they were like, which is the strongest base or which is the strongest, whichever, those got a little iffy.
Oh, okay. Yeah, so which one?
Number 9.
Okay.
And I'm pretty sure I got the right answer, but I just wasn't sure if I was thinking about it correctly.
Okay, let's see. The following 3 equations represent equilibrium that lie far to the right. Identify the strongest base. All right, yeah, so the first choice is the conjugate base of a weak acid. The second choice is an alcohol and it's not very acidic. The third choice is the conjugate base of hydrocyanic acid. So that's a weak acid. So this is a weak base. Water can be either. It's kind of in the middle. So I wouldn't say that was going to be the strongest one. It would be weaker than the first 2 anions. And then NO3 minus is the conjugate base of a strong acid, which makes it very, very weak. So that would probably be one of the weakest there. So it's definitely between choice 1 and 3.
Yeah, that's where I ended up too. I figured that water is probably not ever going to be the answer in these, most likely, and that I pretty much used the same reasoning, but then I got stuck between 1 and 3.
Okay, so let's see what the information they give you in the equilibriums. We have a strong acid with the conjugate base in equilibrium with the weak acid in that spectator NO3 minus. And they tell you that that lies far to the right. Okay, so there's a strong reaction there. Then we have this weak acid HCN with a strong base, and that lies to the right. And then we have water reacting with CH3 minus, and that lies to the right. So yeah, I think you're right. We haven't really talked too much about this one, and so we need a little more time to do that. So I think maybe I should put that homework off until we discuss some of the different possible acids and bases, and then get back to that. So I think I should push the due date for that homework. Let's do it a week from today. That way that'll give us Tuesday to go back and look at these problems after you had a chance to kind of look through some of the stuff more. Yeah.
That sounds good. I started on the notes for the acid and base equilibria ones, which is the homework after, and those seem a little bit more similar to stuff that we've done
Okay.
because we've been doing equilibrium and ice tables this whole time. So it just seems like another step doing that too.
Yeah.
But the initial, this homework, just straight acids and bases, seems like there is some conceptual stuff that I couldn't find any steps for solving for these kinds of problems for like question 9. There wasn't like a system of like, look for this, then look for this, you know, that kind of thing.
Yeah. Yeah. You really have to be able to identify, first of all, acids and bases, and then look for kind of equilibrium concepts about where equilibriums lie, and from that deduce which one is going to be a stronger one, between the two that you narrowed it down to. And so you have to look at those equilibrium problems, those equilibrium reactions, and maybe add a couple together to get an idea of what's happening. So yeah, I'm gonna hold off on that, and then we'll go over this one on Tuesday. All right. Any other problems you want to take a look at? Or maybe we should just go ahead and look at the notes.
Yeah, all of my remaining questions are on that homework, so probably just better to go over the notes then.
Okay, yeah. Then we'll take a look at that on Tuesday after you had a little chance to think about this.
Will both homeworks be due the 17th, or will the second one get pushed until we discuss on Wednesday?
Yeah, we're gonna have to push them both.
Okay.
Yeah. All right. So yesterday, we've been taking our time through this, but we have a lot of time. That schedule was I think a little too fast for us getting through it, but we have a lot of time, like I said, so we're not in a rush. Anyway, yesterday we went over some new concepts, and I probably should just do a quick recap of some of the things that we introduced yesterday. And that was, we started off looking at this table of weak acids and their associated equilibrium constants along with their conjugate bases. The takeaway, one of the big takeaways here was that the equilibrium constant of a weak acid is inversely proportional to the strength of the conjugate base. Then we looked at a few situations where we might need to find the pH of solutions. We would have to write off the bat recognize that as a weak acid because it's not one of the 7 strongs, and we would need to solve that problem with an ice table. B is a strong acid, so we have to remember that for strong acids, we don't need an ice table. It's 100% dissociated, so the concentration of the ions equal the concentration of the solution. In fact, we don't have any nitric acid left. It's all H3O plus and NO3 minus. And then we took a look at what happens when you mix them. When you mix them, it's really just a dilution type of a problem. And then we recognize that the strong acid is 100% dissociated, and any little bit of dissociation that we might get from the weak acid is negligible. And so we don't have to worry about it. And we looked at that and we calculated how small they were. And in fact, it was negligible. This plate was for you guys to read and study. It's just kind of a breakdown of the ice table and some of the important quantities that you can use the ice table to relate to, not only K and Q, but also pH, solubility. We haven't looked at solubility constants yet. That's coming up. Percent ionization we looked at yesterday, which is the same as percent dissociation in this context. Then we said, okay, well, here's a problem. You should cover the answer, try to set up your ice table, and then check these answers. Then we went on and looked at some other problems involving weak acids and how to solve them using an ice table. And we said, okay, we can get around using the quadratic formula and instead check a 5% rule. So we looked at examples of that, and we looked at an example of when it doesn't obey the 5% rule, how much the number changes. Well, it's just a little bit larger than 5% of what we're taking it from. So we have to solve the quadratic because this number is going to change. And when we did the quadratic, we saw that, yeah, it changed to this value. It was still close, though. Then we went on and talked about the fact that the percent ionization of these, for example, weak acids, tend to decrease with the increase of concentration. And we looked at some reasons why it would, at least mathematically. And then we went on to look at polyprotic acids, those acids that have more than one proton. How do you treat them? It turns out that if, well, first of all, we noticed that the equilibrium constants for successive deprotonations always go down compared to the initial equilibrium constant. And then later on, we said that we don't really need to worry about the subsequent deprotonations when calculating things like pH, because the amount of H plus that you get from those is negligible. And the criterion for that was when the magnitude was 10 to the 3 times smaller than the previous. You wouldn't have to worry about it. So in other words, here I have a factor of 10 to the 3 smaller in my second equilibrium constant. So I don't have to worry about any protons that deprotonate from the second dissociation. And we also mentioned that if this second dissociation happened in pure water, you're not going to get much. But if you have a primary dissociation, then that adds to what we call the common ion effect for the second equilibrium, and you would get even less deprotonation because of that common ion effect. And we kind of talked about that yesterday, and we did a calculation showing the decrease in reaction in the presence of a common ion. And that's pretty much where we stopped, right back here yesterday. So are there any questions before we go on? No? Okay. All right, so
Are we about to do, sorry, are we about to do like Ka value to conjugate base value? Is that coming up or?
yeah, that was, yeah, that's what we're leading to.
Okay, I'll wait.
That relationship between the two. We know that they're related and they're inversely proportionally related. But we haven't nailed down that relationship yet.
Okay, no questions then.
Okay, cool. All right, so this slide introduces the equilibrium constant for a weak base. So here is one of the stereotypical weak bases, this ammonia. And so according to Bronsted-Lowry, a base is something that accepts a proton. So this accepts a proton, this base, and it forms the conjugate acid right here, ammonium. And so if this is the base, then this water in this case, which is amphoteric, has to be the acid, because that's going to give up a proton. And according to Bronsted-Lowry's definition, that's the acid. And the thing that's different from it by one proton is the conjugate base. So there's nothing really new about this equilibrium and the definition of the equilibrium constant that follows. Remember, since this is an aqueous solution, water is in the majority. And we represent that sometimes by putting H2O liquid. So in this case, maybe a little bit of that H2O gets used up, but it's negligible. And for all intent and purposes, that concentration, that 55 molar, is constant, and that's incorporated into the equilibrium constant. So you don't see it down here in the definition of Kb, the equilibrium constant for a weak base. So it's not there, it's not represented, just like we did for Ka. But the equilibrium constant is still defined the same way: the concentration of the products to their stoichiometric coefficients over the reactants to theirs. Any questions on that? Okay. Now we have a similar slide here that we had for weak acids before. And this slide is kind of nice because, again, it gives you a picture of the base, and it shows you some of the characteristics that you might expect when looking for weak bases. And it's important, as you know, to be able to identify these weak bases, not only from strong bases, but also from acids, because sometimes some things can act as a base, sometimes an acid. They could be amphoteric. So we have a nice picture of representative weak bases, and we notice some of the similarities. And they're pointed out over here to the left. So whenever something has a negative charge in an acid-base reaction, you're thinking, that, oh boy, that thing could be a weak base. How do you know for sure? You can react it with water and see if it produces a conjugate weak acid. If it produces a conjugate weak acid, then yes, it's a weak base. Another way to maybe identify weak bases is by comparing their structure to ammonia. And so we have ammonia's structure right here, NH3, and we notice that it has a lone pair of electrons on nitrogen. So now we can say, geez, anything that has a lone pair of electrons on nitrogen can act as a weak base because it can accept that proton, just like it does in ammonia to form ammonium. So it accepts the proton, and I can draw the picture down here. You'd have 1 hydrogen, 2 hydrogens, 3, 4 in a tetrahedral, and this whole thing is charged plus. So it accepts the proton, and it can do that because it has this lone pair of electrons on the nitrogen to form that bond, that then the nitrogen can share that pair of electrons with the proton that's coming in to make that new bond. So this has the same feature here as above, and so we can imagine that in the conjugate acid, there's going to be that proton that forms from that lone pair of electrons here, and that's what's going to form the conjugate acid. And you can go on and on and on with this by comparing to nitrogen, and they behave the same way. So you can think, well, geez, there's an infinite amount of possible nitrogen-like, not nitrogen-like, ammonia-like weak bases that have this nitrogen with a lone pair. For example, methylamine, I can just substitute one of the hydrogens here with a methyl group, and it does the same thing as ammonia. And then I can have dimethylamine, or I can make this an ethyl group here, CH2, CH3, and then you can have ethylamine and keep changing all these groups. So you can have an infinite number of weak bases, and they all have their own equilibrium constants. And so you can just look them up once you recognize that that is in fact an ammonia-like weak base. All right. So that's kind of the important of this slide. It introduces weak bases, and it gives you some tips on how to recognize that you're dealing with a weak base and how it will behave when it reacts, for example, with water and takes a hydrogen from the water. The ammonia-like weak bases are going to form cations with one more hydrogen. Now, the negative charge weak bases, again, they can accept the proton because they're rich in electrons, they're negatively charged, and then they form their conjugates with that proton. So these are the two main categories of weak bases that you should be able to recognize in 201. Okay. So you're looking for something with lone pairs, like the nitrogen atom on ammonia, or negative charges. So then it just talks about possibilities in this slide. I have the ClO minus. Oh, it's a negative charged species. It could be a base, so I react it and I see, I get this compound HClO. I'm thinking, oh, do I recognize that as a weak acid? And I do. And so it seems reasonable that this would react in this way. I could look up equilibrium constants, either Ka of HClO or Kb of ClO minus. And there's only going to be one of those, and I'm going to tell you why in a second. Okay. So we want to get to the relationship next, I believe, that's going to show this inverse relationship between the Ka of a weak acid and the Kb of its conjugate base. So on this slide down here, I have that relationship. It turns out that Ka times Kb equals Kw. And Kw is the, as you recall, the equilibrium constant for the autoionization of water. So it's a constant. So now if I look at this equation, I can see that inverse proportionality here. For example, Ka would equal Kw divided by Kb. And you see that, you know, as Kb gets bigger, Ka has to be smaller. All right, so how is this relationship derived? It can be derived with any weak acid and its conjugate base, or weak base and its conjugate acid, by looking at the equilibrium reactions. And this is an example using ammonia and ammonium. But you don't have to do that, and maybe we shouldn't do that. Let's just pick a different one, and then you can look back at this later. All right, let's pick something that's kind of smallish, like HF. Okay. What kind of a compound is HF? Anybody know? Nobody knows what HF is?
Is it a weak acid?
How do you know?
Because you talked about it last slide.
Well, it's got an
It only
H.
has one hydrogen to work with.
Yeah, so it's weak. Now, yeah, that's one of the ones that I spoke about last time. Why isn't it strong? Like HCl, HBr, and HI, they're one of those guys are in the strong acid category.
The bond is really strong with fluorine.
Yes. Okay, but we do recognize it as being an acid. It could, you know, lose that proton. And so if it does and it reacts with water, what's it going to make?
Would it be H3O plus and
Yeah.
F minus?
Yep. And so now you have your acid H3O plus and the conjugate base. So what I want to do now is take a look at the conjugate base and see how I would expect that to behave with water. And I notice it's got a negative charge. So it's kind of in the category of negative charge species that could be a weak base. Could have a nitrogen or something that contains a lone pair of electrons, or it could be negatively charged, and that's what this guy is. So if it's negatively charged, how's it going to react with water? What's it going to make?
It's gonna pick up the proton from water.
Yeah. All right, so now we have our two equilibriums, one of the weak acid and then the other, its conjugate base. We know the definitions of Ka and Kb. So you tell me Ka for HF, I'll just put it up there. What's that going to equal?
Uh, 7.2, 10 to the negative 4.
7.2. Yeah, that's the value that it equals. But how is it
Oh, sorry.
defined? My question was
Oh.
lousy. I should say, how is it defined using the law of mass action?
Concentration of HF times concentration OH minus. Oh, we're doing the
Yeah.
top one. Never mind.
Yeah, you're right. It's the concentration of the products
Yeah.
to their stoichiometric coefficients over the reactant. And I don't include water because that's how the Ka is defined. Now, how about Kb for F minus? What's that equal?
The concentration of HF times the concentration of OH over the concentration of F minus.
Yes, awesome. All right, F minus. Okay, now, what is the relationship between the two? We can get at this a few different ways. One, we can add up this reaction 1 and 2. And when we do that and we get a reaction 3 from it, how are their equilibrium constants related?
You would multiply them.
Yeah, right. And we proved that before, and you can do it real quick by just using any generic A goes to B, and then C goes to D, and see when you add them up and what happens to their equilibrium constants. But that's right. So when I add them up, I see I have an F minus here, 1 over here. So they cancel. I have an HF here with 1 over here, so that cancels. And I see that I get 2 H2O goes to H3O plus OH minus. Do you recognize this equilibrium? It's a special one that we talked about before.
Auto-ionization of water.
Yeah, that's it. So that means this equilibrium constant is Kw. And the first one is Ka, and this is Kb. So we derived our relationship. And that's true for any weak acid and their conjugate base in water, or any weak base and its conjugate acid in water. And we can even show that down here with the definition of the equilibrium constants. If we multiply these equilibrium constants together, we see that this would cross out with this guy would cross out with this, and we would get H3O plus times OH, which in fact we know that's Kw. And so Ka times Kb equals Kw. And so that was done on the previous slide with using ammonia and ammonium as examples. So you can look at that. We did it for this one. And now one of the things that drop out of this relationship is all your textbook and all your reference manuals that tabulate equilibrium constants will only have the equilibrium constant for one, either the weak acid or its conjugate base, and not both, because they figure you can calculate the other one. So you gave me this one here, and now I can calculate KB, because I won't find KB in my textbook, and it'll probably be harder to find online too, but I don't need it. I can calculate KB because I know that KB equals KW over KA. And that's what you gave me for KA. We know that KW is 1 times 10 to the minus 14. That's at 25 degrees. So we don't mention this, but that's kind of given. All these equilibrium constants are temperature dependent. So you got to keep that in the back of your mind. All right. So in this slide, we talk again about that relationship, and we say, all right, now here's an interesting problem, or a problem that you might see down here. So you read this problem, it looks, pretty normal. It says the Ka for HCN, so they give you that, the Ka, you don't even have to look it up. Then they ask you, what's the pH for a 0.15 molar KCN solution? And you're thinking, oh man, is that a typo? Did they make a mistake? Did they mean HCN? And the answer is no, they didn't make a mistake. What you're supposed to recognize is that this is a salt. Does anybody remember from their solubility rules what kind of a salt it is?
It's soluble.
Yeah. Remember group 1 and a lot of the group 2 metals are completely 100% dissociated. That's why they're called strong electrolytes. So now you have to connect some of the stuff that you learned in Chem 200 about salts and say, oh, well, a 0.15 molar solution of KCN doesn't have any KCN in it. There's 0.15 molar K plus and 0.15 molar CN minus. So the first step in this problem is to recognize that there's a dissolution reaction that takes place to completion. And I get the ions. Now, the second thing that you have to recognize is that K plus from Chem 200, that's one of those ions that are 100% dissociation. And so this guy is what we call a spectator. It doesn't react with anything. This guy here, Cn minus, it's got a negative charge. So we just learned that things with negative charges can possibly be bases. So in order to see if it is a base, let's see what happens when it reacts with water. And so it's negative, it's going to accept a proton from water, and it forms this thing here. And of course, it's going to form some hydroxide. And if we look at this, we should recognize that that's hydrocyanic acid, HCN. It's not one of the 7 strong, so it's a weak acid. And so there is an equilibrium that takes place, and this is the equilibrium that you have to identify in this problem. It's this that you're going to have to form the ice table for. So you would form this or you rewrite that out with an ice table using the 0.15 molar as the initial amount of CN minus. And then it's business as usual. Once you have that initial for the ice table, you can fill out the change and the equilibrium. And you can equate it with what we call the type C equilibrium problem. Now, for type C equilibrium problems, we need to look up the equilibrium constant in order to solve for that algebraic parameter X in the ice table. So we go to look up the equilibrium constant for Cn minus, and since it's a base, it's got to be Kb, but we don't find it in the textbook. What we find is the Ka for HCN. And so we calculate the Kb using the relationship that we just introduced between Ka and Kb. We find this in the book, we plug it in, and we calculate the equilibrium constant we need for the ice table that we have to solve the X parameter. And then that's going to give us the concentration of OH minus, which you have to recognize is not directly related to the pH. It's indirectly related to the pH through this equation here. The pH plus the POH equals pKw, which we looked at when we looked at the autoionization of water, or in other words, the pH equals the pKw, which is 14, minus the POH, which we calculated from the problem. So you see, there's a lot of stuff to connect to that we already did, and there's a lot of places that you can go off track here. So when you look at this type of a problem, you're going to have to break it down, and you're going to have to identify the equilibrium that's important. You'll also have to identify maybe some of those initial dissolution reactions that provide concentrations of the ions. Then you're going to have to analyze the ions and determine which ones are the spectators that you can ignore and which ones are the possible acids and bases in those ions. Then once you've identified the equilibrium of interest, you're going to have to remember that I need an equilibrium constant for that species to solve the ice table. Now that may be given, or you might have to calculate it, or maybe you can look it up. And that calculation will be, if you have to calculate it, you'll be using the equilibrium constant for its conjugate. All right, so again, this is the same problem, and it's kind of walking you through of how to think about it, how to break up this and set it out so you can solve it. So you can study the answers again. You know, once you kind of look through it and study it, and you kind of have a feel for what you're going to do, then I would hide the answers. And then go ahead and go through this logic, like, you know, number one, break up the salt. What do you get? A spectator and a possible base. Here's the base. Is it the equilibrium of interest? Yeah, it produces a conjugate weak acid. I need an ice table, and just go through as far as you can. And if you get stuck, then go back and peek at, you know, the approach. But as soon as you get back on the track, then start thinking through that logic again. Then once you finish it, put it away, and then go back the next day and try to do that problem again and think through that same logic and see if you can do it. If you can do it, then awesome. If not, well, that's good too, because you're going to learn how to go about solving these type of problems by going through that logic. And as you do more problems, maybe different curveballs are going to be introduced into the problems, and you'll be able to handle them by practicing. Any comments or questions on that?
So it seems like as long as you can find the pH or pOH of a concentration at equilibrium, it seems to be a lot of the problems. As long as you can reach that point, you have a lot of the ammo you need for the answer of whatever they're asking for.
Yeah, I think that's right. And so far, because that's all the parameters that we've introduced. We've introduced weak acids and weak bases. We've introduced the relationship between their equilibrium constants. And we've introduced pH and pOH and how that relates to each other, as well as the equilibrium constant for the autoionization of water. So that's a whole bunch of stuff you have there to solve these problems. Now, once you get that down, we're going to start introducing other equilibrium constants. For example, the KSP, the solubility product for solids. And you'll see once you have this down that it's just adding another equilibrium constant, but it's the same song and dance. And so you're going to have more weapons and tools to answer slightly variable questions. All right, so this next one is, it's going to introduce us into a really crazy kind of concept that's tied with things we've been talking about. So what I want to do is just introduce this plate. Maybe you can sleep on it, think about it in the background, but then go back and play around with some possible problems involving weak acids and conjugate bases. But anyway, let's take a look at this really quick, because the following plates are going to get into this, but I just wanted to introduce it just to put it in your mind a little bit. So I have a reaction here, and this reaction is an acid-base neutralization reaction, very much like the one that you studied in Chem 200. I have some acid, 2HA, plus a base, some metal hydroxide. That's what the M stands for here. And I see that it reacts and it forms, and you guys know this from Chem 200, water and a salt, right? Acid-base neutralization forms water and a salt. So now we knew that from Chem 200. The questions in Chem 201 that we're going to have to think about now is, one, to what extent does this reaction take place? Is it a completion type reaction? Or does it form an equilibrium? That's number one. And number two, even more interesting, will that solution result in a salty water? That's what you get as products, with equilibrium constant, with a pH that is equal to, less than, or greater than 7, right? So what do you guys think about that second question?
If it's neutral, would it be 7? Because it's neither.
Okay, so if it's neutral, yeah, it will be 7 by definition. But let's say that this goes to completion, and there's a stoichiometric amount of each. So we don't have any HA left, and there's no hydroxide left, because it's a perfect 2-to-1 amount. And so all we have left is water and a salt. Will that salty water result in a pH of 7 or greater than or less than? And I expect you guys to think of one of these possibilities and not the others, because you're coming from 200.
Wouldn't it be 7 because then it's officially neutralized?
Okay, good. That's exactly the result that I would expect you guys to say, having just had Chem 200. But we're going to see that the pH could be any of those.
Is it something to do with finding a limiting reactant or?
No, for this case, we're assuming that they're at a stoichiometric quantities. So both of the reactants are limiting. They both run out.
Okay.
I didn't write it here, so yeah, it's not said, but I'm telling you now, that's what I'm thinking of. And you would think that it was 7, and that's completely reasonable. But in the next few plates, we're going to learn that it can be any one of those. So whenever you have an acid-base neutralization to completion to form water and a salt, you guys from Chem 200 are thinking, pH is 7. But now, once we think about this in terms of what we've learned, we're going to find that it could be any one of those possibilities, which is kind of exciting because now you're going to learn something new that you didn't know in Chem 200 and that you assumed all the time. And sometimes you were right and sometimes you weren't. So I think that this is going to be exciting to get into that next time. But are there any questions before we go back and do some problems involving KAs and KBs?
I think that's really interesting because my Chem 200 teacher refused to really open up any discussion about pH. So you'll get to that in 201. Just
yeah,
wait.
because it's a big ball of wax and it's complicated, as you can see. You have to learn, first of all, about equilibrium and what that means as far as partial reactions and ice tables to see what you have. And that's really complicated for a Chem 200 student. And then on top of that, you have to be able to apply your knowledge and your ability to recognize whether this species is a strong acid or base or a weak acid and a base. And if it is, what is the equilibrium constant that I need to solve the problem? And if I look in the book and I don't have it, then where am I going to find it? And so we're getting our tools to be able to solve really complicated problems like pH of a salty solution. And we're going to be able to solve those after we discuss a few more slides. But anyway, now we can go back to any one of these slides back here that either the weak acid slide or the weak base slide, and we can ask some questions such as, let me get this over here. I'm going to need to get rid of this. All right. Now, let's say we have let's say what is the pOH of a 1.5 molar solution of ammonium nitrate, aqueous. All right, that's looks innocently enough, or innocent enough. We want to find the pOH of the solution. Okay. How should I go about thinking about solving this? So I need to, first of all, figure out what I have in that solution. So what do you think? What should I do? What is in a 1 molar solution of NH4 NO3 aqueous? If I had like a beaker and a microscope that can see in the atomic level, which I can't, but if I did, what would I see in that 1.5 molar solution? Anybody?
Water would be in there.
Yes, mostly water, H2O. What else? Let's see who remembers their solubility rules. Well, this is good. You guys need to look back at your solubility rules from Chem 200. Make a note of it. So what happens to this when you put it in water? I mean, it's already in water. So what's in the beaker?
It's gonna be ammonium ion and nitrate ion.
Yeah. How did you know that?
From solubility rules, soluble.
Yeah. Okay. And that's the only way you know it, right? You know, this is one of those cases where it's completely soluble. You look back at the solubility rules and you see that anything with nitrate completely dissolves into its ions. And I think ammonium is the same way if you look back at the solubility rules. So you have pretty much ammonium floating around, aqueous, and you have nitrate, aqueous. Now I'm trying to find the pH or the POH of this solution. So I'm going to need to figure out what the concentration of OH minus is, hydroxide. And I know in pure water, it's 1 times 10 to the -7, so it would be 7 in pure water. But I have these ions in this solution. Do I recognize them as acids or bases? Are they going to react with water? I see that this is negatively charged, right? And I see that this is positively charged. And maybe I even might recognize this as being an acid or a base. What do you think? What is ammonium?
Would it be an acid?
Okay, good. It is. But what gave you the idea that it was an acid? What is it, the acid? Can you identify it, any connections between that and something else that would verify it?
Well, we just talked about how ions with a negative charge would be a base, so I just guessed.
Yeah. Okay, well, you guessed right. But look back here on the other page. Ammonium, NH4 plus, is the conjugate acid of the weak base ammonia. So it is an acid, and it's going to form an equilibrium with ammonia. So it will react with water and make a little bit of ammonia because they're both weak. And when you have a situation where you have a weak acid and its conjugate base, they come to equilibrium and there's a mixture. Okay, right? That's what we've been saying. And that's how you can identify one from the other. They're connected. All right, how about, so we see and we're sure now that this is a weak acid. So that's going to have an equilibrium table that needs to be solved, and we can calculate concentrations of ions from that and be able to solve for the pH. But how about nitrate? What could that be?
a base,
Okay, could be a base. What makes you think so?
the negative sign.
Yeah.
And then it has nitrogen.
Yeah. All right, cool. So we have a weak acid and a possible weak base. Now, how am I going to check to see if in fact that is a weak base? I better react it with water and see what I make, right? So if it's a weak base, what do weak bases do according to Bronsted definition?
They accept a proton.
Okay, cool. So if it accepts a proton, I'm going to make this. And it looks like, yeah, it would produce some hydroxide. Okay, so I recognize this. What is this compound?
Nitric acid.
Yeah. What is it?
Nit
Yeah, that's nitric acid, right? What kind of an acid is that?
strong acid.
So do strong acids form in aqueous solution or do they completely dissociate?
They dissociate.
Yeah. So this reaction doesn't produce a strong acid. In fact, the equilibrium lies so far to the left that this conjugate base is considered to be a spectator. Because you don't form strong acids, they break up completely. That means that its strength, its Ka, is so big, 1,000,000 or more, that this Kb is so small that it doesn't react at all. It's a spectator. So the conjugates of strongs are too weak to react. We call them spectators. So I can ignore this ion. It just doesn't do anything. It's just taking up space. The real equilibrium that I have to concentrate on to answer the problem is this one. So I'm going to first realize that through inspection and logic and all using all the techniques that we learned so far, and deduce the fact that this is the reaction that's of interest for calculating the POH. So I have initial delta equilibrium. This is a 1.5 molar solution. These I don't have to worry about. Initially, this starts out as 0, and then I get a little bit as it comes to equilibrium. And now I need to calculate X. And if I can calculate X, I can calculate the pH, and then I can calculate POH because I know POH equals pKw minus pH. Okay,
Is
so
that
far so good.
bottom one supposed to be 1.5 minus X or just 1.5?
Oh, yeah, sorry. Thank you. Yeah, I forgot my minus X, which I'm going to ignore in the solution anyway and invoke the 5% rule. But thank you for pointing that out because it was not correct. All right, so anything else? So far, so good. Okay, so now I need an equilibrium constant because I know for this reaction, that equilibrium constant is going to equal x squared over 1.5 minus x. So what equilibrium constant am I going to look for? What's it called?
Ka,
Yeah, Ka for,
ammonium.
yeah, for the ammonium. And I look in my textbook, I can't find it. I look online, I can't find it. What do I do?
use the NH3.
Yeah, I use the KB for NH3. And I know what that equals. So the KW is 1 times 10 to the minus 14. And the KB, which is in the book, and it's also over here, 1.8 times 10 to the minus 5. And now I can go ahead and calculate X. I'll neglect it here and check the 5% rule. And calculate X. I'm gonna punch all these numbers in my calculator. So this ratio here equals 5.6 times 10 to the minus 10th. And so if I multiply that by 1.5 and then take the square root, I get X 2.9 times 10 to the minus 5. And I know that that's way less than 5% of what I neglected to take it from back here. So the 5% rule's good. You can check it. And now that tells me that the H3O concentration is this value. And so now I can calculate the pH by finding minus the log of that, which is 4.54. And I know that 14 minus that is going to give me the POH, which is 9.46. Okay, any questions on that? So I think you want to go back and study these, see how those equilibrium constants can be used in different cases, and also maybe look at some more problems involving salty water solutions. And you have to analyze the cation as though it might be an acid, the anion as though it might be a base. How do you analyze it? You go ahead and react it with water, see what it makes. If it makes a strong, then it's a spectator. If it makes a weak, whether it's acid or base, then that's the equilibrium that's going to engage, and that's the one that you want to use in solving your problem. And in Chem 201, there's only one. There's one or none, as we'll find. And in the none case, that's just one of those Chem 200 completion reactions, and so the ions are whatever concentrations they are. There's no equilibrium, so you just use your limiting reagent techniques to calculate the pH or POH. All right, any questions on anything? Then I'm going to